and welcome to the 12th video on a series about topology. Now, if this comes up on my channel right after the third video, it's not an accident. It's because I'm actually filming this right after the third and alongside the fourth, and I had an idea to film the chapters strictly on logic and set theory, which is more or less the entire first part of the book that I'm using, Munger's Topology, the first 11 chapters/videos, while I go through the real heart of the matter, which is topological spaces and a real look at topology, starting from chapter 12 onwards. So I think the necessary basic set theory definitions and operations on sets and everything were sufficient to really lead into what's being stated here. And yeah, so that's going to be the plan, hopefully, where if we need a concept that does arise in some of those chapters between 3 and 12, I'll have uploaded it by the time we actually need it in a later chapter. So this is about topological spaces. And the history of topology is quite a rich and fascinating one, where quite a lot of mathematicians spent time thinking about what would be an appropriate definition for a topology. Like, what is something that is sufficiently general, but something that is specific enough to fit our needs, that is like something that's abstract yet able to be handled in a concrete way, where one can cite properties that are familiar yet easily generalizable. So we're going to look at just the definition of a topological space, and I think that will invariably seem a little bit abstract at first, but I hope that the next few videos will clarify how to work with topologies and topological spaces and really get a handle on what's going on here. So let's briefly motivate. As I'd said in the first video, topology is about continuous deformation, that is, spaces and kinds of I don't want to say mappings yet, but just kinds of continuity. And a topological space is going to be a set with some more structure, and this additional structure is called the topology on the set, which allows defining continuous deformation of subspaces. This probably seems, again, a bit abstract here for no evident reason yet, but we're going to go ahead with the definition and hope that you build an intuition on what topologies look like. So a topology on a set X is a collection tau of its subsets. So if you want to think of, like, I don't know, tau as elements of its power set, that's an equivalent thing, but a collection tau of subsets of X that satisfy the following. And there's 3 axioms that one must check for something to be a valid topology on a set. So you're given the set, and the first condition is that the empty set and the whole space, or the whole set X, both nothing and everything in a sense, is going to be contained in tau. They're both subsets, first of all, of X, so we know that doesn't raise any issues, and that's the first axiom. The second one is that the union of any subcollection, that is a collection that is contained in tau of sets, you can take unions of any subcollection and still have that set be within tau. One can say that it's closed under arbitrary unions. And this is an important distinction that I'm actually going to raise now, right after defining this third behavior or axiom of how topologies act under this other operation that we're familiar with of intersections, where if you take a finite subcollection, strictly finite, of tau, and you take across all of those finitely many sets their intersection, then your resultant set is going to be in tau as well. And the difference between axioms 2 and 3, and the reason why I point that out, is because in 2, this union can be taken over arbitrarily many sets. It need not be finite, it need not even be countable. It could be anything. So it could be infinite or uncountable or anything you'd like, so any subcollection. But 3 is more stringent. That is the requirement for taking intersections and it being closed under these. This is called the finite intersection property, and 2 might be called the arbitrary union property. So this is the difference here. Let us just talk about now quickly like why this video is named a topological space. So essentially a set X that has a topology tau which has been specified on it is a topological space. So if you have a set and you're able to specify some collection of subsets of X that satisfy these axioms 1, 2, and 3, then what you've just done is defined a topological space. And if we want to be formal about it, we would denote a topological space as like an ordered pair, for example, of X comma T, because that comprises all the information that we need or that it's giving us about the topological nature of this set X. But typically when the topology is unambiguous on a set and it's clear from context that we can just omit like the ordered tuple or a formal definition, we will just refer to the set itself as the topological space. So we might say like let X be a topological space. And while that's not strictly the most precise definition of it, it's usually clear that, of course, we're implicitly defining some topology tau on X. So that's what we have here. And now we have a definition. So if X comma tau, and I just wrote this for completeness sake, is a topological space, and we have some set U in the topology, and the only condition is that it's contained in the topology, then U is by definition what we call an open set. Now, some of you may be familiar with open sets, having worked with them maybe on like, I'm not sure where, but certainly for analysis might be one of them, thinking about open sets. And it's actually that a lot of the results in analysis come from defining a certain kind of topology, looking at the topological properties of the real numbers. That is, one can actually think of the real numbers as a space where you can define a notion of distance and think of it like a metric space. So the metric space nature of the real numbers actually pertains to its topological properties, and we call that the metric topology, and we'll rigorously define it later, and it'll be very useful and interesting. But yes, with that example, we have the metric topology, and in fact, by definition, all of those sets that we thought of as open are literally defined as open sets. So it's a more general definition than what some may have seen outside this context. So that's the open set definition. And here's an example where we show that open sets are kind of more abstract than what we think of as maybe like neighborhoods in the real numbers, just like kind of the open balls about a point. And we do this by taking like a really small example and showing that, in fact, we can define a topology and checking those 3 axioms that we need to satisfy. So let X equal this 3-point set, discrete 3-point set A, B, C. And we can define a topology on X of these subsets in particular. And the first axiom said that we needed to have the empty set in X. So we have to include those where X is A, B, C. So those 2 are by definition in any topology. And then we have these 3 auxiliary subsets, which will say A, B, B, and B, C. So first we want to check arbitrary unions. If we take unions across, of course, anything with X is just going to give X, and anything with empty set is just going to give that. Intersections, vice versa, you just get a null set if you take intersections with it, and you get the set itself if you take intersections with the whole space. So let's just look at these 3 sets and take unions, and fortunately all intersections are finite here. So starting with unions, you take AB with B, you just get AB. You take AB with BC and you just get, you take AB union BC and you get the whole space X, right? You take A, B, and C. So that's your union. And then B and BC is just BC, right? So those are our 3 unions we need to check. And then as for intersections, you take AB intersects B at just B, AB intersects BC at just B, because they share only the point B, and then B intersects BC at just the point B. So we've actually just verified all of those, although a bit loosely, and I encourage you to write it out fully, that this in fact satisfies the definitions of a topology. So these are, this is kind of one construction we can do on 3 points And it's a fun exercise, actually, just beyond this, kind of exploring what kinds of topologies you can have. Like, there are only so many subsets that you can make for finitely many, or sets of small cardinality, like 3. You can only have, what is that, 2 to the third, so 8 elements in its power set. So 8 subsets, and you can play around with which ones define a topology, which ones don't. It's good to get an understanding of the way that these axioms work. So that's that. And now we're going to define 2 important topologies, constructions on a set, which are sort of like dual to one another. That is a formal term, but I sort of use it loosely here, that these are kind of 2 examples of almost ridiculous topologies that we will never use, really, but it's important to note that they're there, and they're actually important for counterexamples sometimes as well, which can be oftentimes more useful than examples. So if we have X to be any set first, let's take X to be any set you'd like. Just define one is what we call the discrete topology on X. And this consists of all subsets of X. The reason, I guess, why it's called discrete is that it's treating every subset as a point. So really, this is just a collection of points, and you're not thinking of it as any more or any less. These subsets of X. And of course, this is going to be a topology now, if we think about it, because the space X is a subset of itself. You have the empty set, a subset of any set. And taking arbitrary unions and finite intersections, one can think, well, if we have these subsets of X, there's no way for me to take unions or intersections and end up outside the set X, so to speak. You're always going to remain contained within X, and taking these operations will always give you another subset. So it's closed in that regard, and that's one example of a topology, a rather extreme one, where you're taking all of its subsets. So that's one way. And the second one is kind of counter to this, because we want to think about what is the minimal construction, like what is the least amount of sets in any given in any given topology, such that it actually just satisfies those axioms, right? So we take a look back here at 1, 2, and 3, and we assess the first one, where we have the empty set and we have X. And we stop for a moment and say, well, is that enough to define a topology? And it turns out that it is enough, because taking unions of any subcollections, of course, this only consists of now taking unions of empty set and X, which of course just gives you X. Likewise, intersections are just this and intersection this, and since the intersection of the empty set with any other set is also the empty set, that is by definition contained in the topology. Hence, this is sort of the smallest construction, or the most efficient construction, if we want to look at it like that, of a topology on any given set. It's like we have the discrete topology to be as full as possible, and we have the indiscrete topology, which we call here as like sparse as possible, maybe. So these two are counter to one another, and they're kind of the extreme ends of topologies. Okay, so here's a more robust example which can really illustrate the process of how we might check these axioms in a non-trivial case, or one that's not like with 3 points where you can just do it by testing each case individually. So we have what's called the finite complement topology. And as its name suggests, if we let X be a set, we define this topology by declaring all open sets as having complements in X that are finite. And this maybe seems a little awkward, because really what we're doing is defining this topology based on complements of the open sets, which in a later video we'll divulge more information on. These are called closed sets. So for now, we'll just focus on this definition here. So collection of all subsets U, where X minus U is either finite or it's X itself. Now, we want to check that tau sub f is a topology. To do this, we just run through our axioms. So 1. we want to show that the empty set and we want to show that X as a whole space are both in tau sub f. So why is this the case? We are looking at a suitable choice of U for each one. And in each case, now we take U for the first one to be X itself, because X minus X is just the empty set, and that is, of course, by definition, finite, right? So this is our first choice, and then to show, as you might have guessed now, X itself, so sorry, we take U to be the empty set. So now we have the X minus the empty set is just X, and this satisfies the second condition, so that it's X itself. So those are the two prongs of this part, and we've shown that first property. Now we might use a bit more machinery for parts 2 and 3 about arbitrary unions and countable intersections, and let's look at the second one first. We let this family of indexed elements of tau sub f, and I'm realizing now as I say this that I might not have aired the video yet where I go over indexed families, but the important thing to note here is that there's arbitrarily many or arbitrarily few an arbitrary amount of elements that we're just indexing by alpha. That's all there is to it. So it's just this this indexing alpha to denote a family of sets, and in this case non-empty elements of tau sub f. What we want to show is if we take the union across all of these sets, that we in fact have something that is still contained in tau sub f, with the important property that X minus U is either, for all U in this collection, it's either finite or X itself, right? So we use De Morgan's law, actually, which you'll recall from the first video, where we take, to show that this is in tau sub f, we take the complement, and now we have that this is an intersection. So the complement of the unions is the intersection of the complements, which is the verbal statement of De Morgan's law. And this latter set over here on the right-hand side is finite, because you're taking an intersection across sets that are finite by definition of this X minus U property, where U sub A is in T sub F. You have to have this side finite. So if this intersection is finite, and then we have this is finite as well. So that is the first part where we show that this complement of the unions U sub A in this family is itself contained in the topology. So we use a similar idea for intersections, where now we take finitely many indexed by natural numbers, so U1 through U sub n, which are non-empty. And here we employ De Morgan's law again, but sort of for the opposite effect, where we now take the complement of the intersection as the union of the complements, and we show the set on the right hand side, which is a finite union. Now we see the finiteness condition being important because it's from 1 to n, where n is not it doesn't go infinitely. So we need to have this to be finite, right? Because we're taking a finite union of, by definition, finite sets here. So is this, which means that this whole intersection here, by definition here, must be in tau. So we have these three checked, and in fact, the finite complement topology is a topology on X. So actually, I left a little note here as an exercise. One might think about, instead of just finite, the condition, the complement of a given set is countable for it to be considered as open. And it's good to work through this, because this does in fact induce a different topology called which I called here the countable complement topology. I'm not sure if it has a name, but just using the convention of finite complement. Yeah, so that's useful. And we end this chapter now with a final definition where we're thinking about now how, since we've defined a new object, we want to think about how to really compare them or relate them to one another. And we let tau and tau prime be two topologies on a given set X. Now, we introduce this bit of terminology where if tau is contained in tau prime, that is, if every set in the collection tau is also an element in, or is also a set in the collection tau prime, one considers tau prime to be finer than tau. Respectively, tau is coarser than tau prime. And there's a little bit of ambiguity here because some mathematicians might use larger and smaller, and some might actually switch around the ideas of finite and coarser, of finer and coarser. And the way to think about this is that really the example that's used in the book is a truckload of gravel that gets smashed all onto the concrete, and now you have smaller and smaller pebbles. And if you have more and more open sets, that is, if you have more a finer topology, you think of the coarser one being contained in the finer one because it's larger in a sense, the finer one. So with that truckload of gravel analogy, smashing to smaller and smaller pebbles being the open sets, right? And respectively, tau is coarser than tau prime. Now, in either of these contexts where one can establish this kind of inclusion relation on two topologies, they're considered comparable. So either if tau is coarser or if it's finer than tau prime for any two given topologies. So these are our last definitions. And that has been the chapter about topological spaces and the first real foray into the study of topology. I hope you found this interesting, and we will continue with more fundamental concepts in topology in the next video, which will cover a basis for a topology. Thank you for watching, and we will see you in the next video. Sorry.